That's the one. It's like I gave us an assignment. I did not. Okay. So we are actually looking at there's a project that we're supposed to be given after the whole of the data modeling techniques, which we have covered, starting from, you can go ahead, starting from, you can just take one of the cutting up. I can just have some light. So, yes, sir. So there's a project here. I will just show us the projects, and then can go and work on it, and then after some time we can come back to the solution, but we will just continue with a new topic. But like I told us the other time, once we round up this unsupervised section, we will start looking at the supervised, where we're looking at the predictive analysis, and for us to also utilize the skills we are learning. The essence of the unsupervised is to perfect, to model, to structure your data for modeling, or to be passed into the analysis model. Trying to look at maybe in same projects. All this. Now, I will just show us the project, then you can, I will give us the data you are going to work with. You can give it a try and see if you can, because the essence of the project is to walk you through all that we have covered under the data modeling technique, starting from clustering to which other one again? DB scan, hierarchical, right? So that's the project is to walk you through. So this is the project. So this is like you are given a job to do for an organization. So the project is like a job assignment base. Let's say as a data scientist for Northwind Trader. So this is the name of the company. Do I have to put it in a bigger view so that you can see it better, right? Are you seeing it like this? Let me put it in the alpha. Is it okay like this? Okay. So you just want to get a concept, what is required from us. A wholesale distributor that supplies government food products to restaurants, cafes, and specialty food retailers. The assignment, you have access to their yearly client reports, which is the data set that I said I'm going to give to us, which include the channel and region for each client, as well as their total spend by product categories in the last year. Your task is to use clustering techniques to understand the different client segments so the company can better cater to and support each type. Then the objective, scale the data, apply 3 different clustering techniques. Then compare the segments using C-hot score. Remember, we talked about that. Now, this is expected to walk you through the data I'm going to give us. This is just a brief of it. I think I should allow us to go with the assignment because this is actually the solution. So I don't want to consider the solution today. So if we are to write, maybe we should write so that once you get the data set, let me see what you can come up with, because I want to actually go to a new topic. So when you come back with the solution, we'll go through it together instead of spending the whole of today for the project. So this possibly is the project you have to take time. It requires you going back to everything we have covered to refresh yourself before you can perform some analysis or perform some restructuring. So let me give us some time to write out just this slide content, and then we move on. All right, so we are looking at a different topic, which is part of what we need to learn under unsupervised learning, probably the ending part of it. And it's very important to understand that concept as well. And it is called dimensionality reduction. You remember when we started the program, it's part of the arms of data, it's part of the unsupervised machine learning. Dimensionality reduction is part of it. I think I need to stay on the bigger view because we have a lot of slides to go through. So dimensionality reduction, that is a topic. So what I intend us to know in this session is the theory behind it. And then probably our next meeting will look at the application, because there are lots of theory that we need to know about this so that at the end of the day, it will not look like abstracts. We need to understand what the function will be doing and how the function will be, or the library will be performing their calculations. So in this session, we will introduce the fundamentals of dimensionality reduction and cover 2 popular techniques. So we need to know the 2 popular techniques used in dimensionality reduction, such as the principal component analysis presented as PCA, and the TSNE, which means the T distributed stochastic neighbor embedding. So these are the most used techniques for dimensionality reduction. So what is our goal for this session? Our goal is to review where dimensionality reduction sits within the data science workflow. We are also going to learn how popular dimensionality reduction techniques fundamentally works, and then also apply and interpret the results of PCA and TSNE model in Python. So that would be our major focus. Now, there might be a little contradiction with the concepts we have registered under data prep, that is under data preparation. You know, there was this concept that we adopted under data preparation, which talks about you are going to tell me the right right word, but I will just break it down. When we talk about where we learned how to reduce row granularity, right? Row granularity. So I was talking about data selection, right? Where we ended up reducing or deleting an entire columns, but the concept is not the same thing. There are two different things. And as I walk all through the entire process, you will see the need for adopting dimensionality reduction concepts as against what? Feature selection, which falls under the row granularity. So let's look at the definition. Dimensionality reduction involves reducing the number of what? Columns. Good. Reducing the number of what? Columns, which means what? The dimension in a data set while losing what? A little information as possible. So the diagram on the screen has explained it. This is one of the data sets we worked with the other time when we were dealing with the clustering and the order, right? Now, the first data set by my left-hand side has how many headers? Books, TV show, and the video what? Game. That is 3, right? Now, under data selection, what we did is that we deleted an entire column from the data. But here we are not deleting. Though you are losing little information, but that does not mean that you are deleting. Instead, you are compressing. So you can see that the whole data set initially having 3 fields or 3 features have now been compressed or reduced to what? PC1 and what? PC2. So what happened here, like I've indicated there with the notes, the PC1 and the PC2 columns each hold a combination of information from the books. I'm trying to highlight the header. So the information you are seeing under this PC1 and PC2 holds information corresponding to what? Books as a header, TV show, and video game column. So actually, we have not actually lost those information. We have only compressed them in what? 2 columns. Now, how is this different from feature selection? Feature selection involves dropping what? Entire column. But dimensionality reduction involves transforming the original what? Column. That is one of the main differences we should note in the field of data science, still under unsupervised machine learning. Now here, I'm still trying to use, can we still remember this type of graph? The one by my left-hand side. What type of graph is that? That was when we visualized one of the under K-mean or hierarchical under what? That's the 3D, right? Now, this is, I'm trying to visualize it so I understand what we are saying. Now, here is still the construction of that first node. Now, I want us to look at from the first where you have 3 dimensions to where you have 2 dimensions. Which one do you think? You can see that what we have here is that the informations are, they are better clustered in the 2 dimensions. Have we noticed that? They are better clustered in 2 dimensions. But when they are in 3 dimensions, they are not what? Clustered at all. It's as if, because we cannot actually say, okay, this is one group, this is what? Another group. Now, the point we are making is the use case of this whole concept called what? Dimensionality what? Reduction. Why should you, as a data scientist, apply it? It helps you to easily what? Cluster your what? Your data. Point. Are you with me? That is what we are trying to picture out with this whole diagram. So when next you want to cluster your information, your data, then it is best considering what? Dimensionality what? Reduction, because that is what these 2 diagrams are actually showing us. Now notice how with what? Fewer dimension, it's easier to see clusters in the data. I remember there was this heat map visualization we did that was actually confusing us in terms of interpretation. And from what we did, you notice that the more clusters, I think I give that advice. There is something that led to us using what? Heat map, right? And I said the more clusters you have, then the more complex the interpretation becomes. And that was the reason why we recommended heat map, that in case your cluster exceed 2 clusters, then you have to adopt what? A heat map method for you to be able to segment them. So all these are steps towards making your clustering what? Easier. That is what we are trying to. So why? Let's look at some of the reasons. Why reduce dimensions? Why? In the field of machine learning or data science, why should reducing dimension important to us? What exactly are we trying to achieve? These are the points I'm trying to register here. So reducing the numbers of dimensions in a data set helps with these issues. Number 1, EDA, which means exploratory data what? Analysis. Under it, I specified that it is difficult for human to visualize data with more than what? 2 or what? 3 dimensions clearly. So it was not too bad when some of us reacted the other time that this thing is confusing. So you can see, you can now begin to see some of the reason why it was confusing, because at that point, you did not what? Apply dimensionality what? Reduction. The solution, if we are saying that it is difficult for humans to visualize data with more than 2 or more dimensions clearly, then what should we do to make it easier? The solution here is what? Using dimensionality reduction, that is where we have 4 plus column can be reduced to what? 2 or 3 is the solution. And you are not actually deleting the entire data. You are only transforming, like I have established before. So another reason why we should reduce dimension is for supervised learning, which I said is the final phase of this entire machine learning. So right now we are still under unsupervised. So even when we get to that aspect, reducing the dimension of our data, we have the predictive models fit on wide data does not perform as well as those fit on what? Long data. So what is the solution? The solution is what? By reducing dimensions in features engineering, the data gets narrower. So another reason is unsupervised learning. Data points spread out with more dimensions, and their distances become more similar because of what? Dimensionality. That is why you should think of reducing. When the data dimension, when the columns are too much, that is one of the challenge we face under unsupervised. Then the solution is still reducing dimension that is recommended. So by reducing the dimensions, distant calculations become more meaningful. So these are enough reasons why, as a data scientist, when you are given data sets that have so many columns or features, you should consider adopting dimensionality reduction in order to enhance this entire process. All right. Now, let's quickly look at the dimensionality reduction in data science workflow. You know, we discussed something of this nature, this kind of structure under data prep, where I highlighted the 6 modeling what steps. Now, we are trying to, if you remember, this was the same diagram. And now we are looking at what points will dimensionality reduction become useful in this workflow, or the 6 different workflow. Now, as you can see, under exploring data and what modeling data, that is what the 2 steps before the last step. That is where you will definitely involve this entire concept. So under exploring data, can be used, that is dimensionality reduction can be used as a machine learning alternative to what? Data visualization. Just to explain further, data is typically visualized using 2 what? Dimensions, X and y-axis. By using PCA or TSNE, high dimensional data can also be visualized in 2 dimensions. So like I said, everything I'm going to discuss today is the theory behind this concept. In our next session, we will go straight to the practical application. Now, what this knowledge will help us to achieve then is for us to understand the working of the entire library and the functions that will be involved. Now, under data modeling, how does the dimensionality reduction helps? It can be used for feature engineering when preparing supervised learning. So feature selection or engineering is typically done manually by removing features or applying transformation to create them. By using PCA, multiple fields can be mathematically reduced to fewer fields, which it is called feature extraction. So still on how it can help in data science modeling, it can be used as an unsupervised learning technique for recommenders. Recommenders is still part of what we are expected to learn. All right, so here I'm still trying to give the breakdown of the dimensionality reduction workflow in data science. So the general dimensionality reduction workflow consists of the following steps. So here I'm highlighting the steps that we'll be following for us to apply these concepts. So the first step is going to be data prep, and I don't think we are new to this. So most of them we just like to mention them so that you can acknowledge them. So at this point or this step, we'll be getting our data ready to be imputed into machine learning model. And then modeling, applying dimensionality reduction techniques, and then tuning, evaluate and tune the model using metrics and intuition. Then selection, pick the best results and identify any insights. So these are still within that you can see where the concept comes in. All the concepts that are mentioned under dimensionality reduction comes under what? Modeling. The 3 of them are mentioned here, or the 2 popularly used method or techniques, they are under modeling. So that is where you are going to actually implement this entire concepts. Now, just to explain further, so here, let's quickly look at it properly. So here, we are now discussing the principal component analysis, which is the PC. Yeah? Yes, under dimensionality. What we are doing is just try to give the application, but now we want to focus on it. And then we advise us, we sketch the diagram as we go to give us a better understanding. So principal component analysis, PCA, is a dimensionality reduction technique that defines linear combination. I want us to underline the section that is describing the key function. It's a dimensionality reduction technique that finds linear combination of features. The word feature in this case, what does it represent? The headers, good. Features that explain the most variation in the data. So if you look at this diagram that we have here, this is where you can say we are using the straight line concept. So you will just be ruling different lines. Let me see. Yeah, you just be ruling different lines. And then each time you rule a straight line, you look at the field you look at the variation of the fields. That is what will determine the PCA category. Now remember that the PCA here is just like grouping some headers. That is where the transformation comes from. One of the slides that I showed us where we have those three columns or headers that we ended up dimension into PC1 and what PC2. And I said, then we are not totally deleting. What we are doing is transforming. And then the whole of this is what's here. We have y-axis, right? And then we have what? S-axis. So which means that this is one column, for example. But this line is what is denoting the columns. So when you rule this line, how many features can associate with the line that will determine the reduction? In this case. Now here, we have been able to collapse what? From 2 dimensions to what? Just S what? Dimension. Which means that before you get to this state, you must have reduced what? The headers. And the logic used is what? The line. This line that we rule like this, we are going to be changing it. And then each time you change it, it will give you what? Different number of headers. Until we get to a point whereby we have the what? The highest reduction that we can no longer reduce. Then we can now pass it into our model. So let's look at the principal component analysis. We are trying to highlight the way it works, the steps that will be involved. So principal component analysis PCA is a dimensionality reduction technique that find just like I've defined before. Here we are focusing on how it works. The way it works is we can still be capturing that diagram that I showed us. You start by creating a scatter plot and find the center of the data. So like I started by saying, this is just like explaining the theory of what? The dimensionality reduction. Because we are going to use Python inbuilt library functions to implement all this. So we are not going to be doing this manually. Now, once you have created your scatter plots and also find the center of the data, the next thing that will happen is tracing a line through the center. So capture that diagram that I showed us now. Trace a line through the center that captures the most spread or variation in the data. This is the first principal component, PC1. So this is how we are going to arrive at what? PC1. We are going to rule a straight line, and then we'll find out the spread, the variation of the data. Then step number 2 or 3 rather, you create another line perpendicular to the first one that captured the most spread or variation in the data. So this is the second principal component. So this is how we are going to be getting PC1, PC2. It means we are going to be creating different lines. And each time you establish the line, you find out the variation in the data. Then number 4, you repeat the step 3 until you have as many principal components as original columns. Then step 5, to reduce the dimension, keep a subset of the principal components, e.g. PC1 only. So at the end of the day, after comparing the level of different variation of the data, aligning with the line you move, then you come to one that you pick. And when you pick that one, it means you must have. So example of the use cases, visualizing clusters in fewer dimensions to spot check clustering segmentation results. We can adopt this. Improving a model predictive power by reducing redundance or unnecessary dimensions. So all this can help in improving your predictive model if the dimension is reduced. All right, so this is the demonstration of what I just explained. This is where we create a scatter plot and find the center of the what? The data. So the green here or blue dot here is what is representing the center. And then once we identify that center, the next thing is for us to rule a straight line. And then this is where you rule the first line, like we have explained before. This is your step 2. Trace a line through the center that captured the most spread or variation in the data. This is the first principal component represented as PC1. So I will encourage us to be drawing the line because we have a lot of them that I will be bringing to explain different PC as principal components. And all this logic, they are geared towards reducing the dimension. This is the logic behind the function. Now here, this is still the same step. We rule a perpendicular line, like I've also explained there before. Are you still writing on the first slide? Can I go back? Look at this. This one is the second step. This one is the first step, right? We have step 1 where you create a scatter plot. And then what you do is that you identify what? The center of the data in the scatter plot. Then you rule a line that crosses that center. Yeah, this is step 2. Now, even this is still part of what? This step 2. You know that we are just changing the line. We are just changing the line. Yes, we are just changing the line. Like I've highlighted before, this perpendicular line, we are trying to see the better way we can reduce the dimension. That is the whole idea of. So this is what the function will be doing at the background with our data set. So each time it rules a straight line, it will assess the level of what? Data variation. So at the end of the day, that is what will determine the dimension reduction. So this is, I think this one is still like the other one. Then this is another one. But what is happening here is project each point onto the what? The line at an angle of what? 90 degree. So it's still the same logic we are trying to explain here. Then here we have once you project that, so here we are beginning to look at some calculation that will be happening behind the scene. So you're going to solve the square distance between the projected point and the center. So as we can see here, the first center line that you established was the one with, is it the green or pink? What color is this? Can I say green? This is not green. Now, the black that is on that line is where you are measuring what? The distance. So we are going to sum the square distance between the projected point and the center. So all these are the logic. Like you can see there, D1 square. That's what? The distance, the square of the first distance. Now, if you check here, this is another line, and you capture another what? Data point. And this is labeled to be what? To be 2. So you add it together. This is what the function will be doing, to be adding it up. Then this is where you are still projecting, and then summing them up, then still projecting, and then still projecting. Then finally, you get what? The value 4.8. Yes, yes. Yes, all these points that are on the line. On the line. So the idea is that as you are ruling the line, you are changing the location of the line, more data are being captured. And anyone that is captured, you are squaring the sum of it. That's from the point, from the center. That is why one of the steps is identify the word, the center. So once you identify the center, you now know the number of data points that are captured from. Now you are now calculating the distance between the center and the data points you are capturing. That is the logic. So like I said, this is all trying to understand what the function will be doing. It's function that will actually be doing all this. But when we arrive at any answer, we will now know what must have happened. That is why we are going through the theory. Now, here, you can say it here, find the line that maximize the sum of the square distance. So we want to now look at how we are going to arrive at the dimension reduction now. You find the line that maximize the sum of squared distance. Why maximize the distance? This guarantees that the principal component line capture the most variation in the data. This we need to be taking note of this important aspects. All right. Now look at it. Now we are trying another line now. We are trying another line. So if you look at it now, I've changed the direction of the line. So here we want to try another line. And then you see that when you change as we change the line direction, we capture more data that have increased the total now. You can see it here. So this is the center. So note that the points are more spread
out now as we change the line. Whether which one is better? Yes, yes. There is no, what we are looking at here is that the concept we have established for that what? How do you end up reducing the dimension? Is by ruling what? Linear what? Lines. Straight line, perpendicular line, and then also observing the number of what? Capture what? Data points. So this is just like illustrating that the more you do it, then to get to a point whereby when you rule another line, after you try different lines, you get to a point whereby you rule a line and no data point is captured. So at that point, the function will assume that what the feature that is able to capture that time is the one it's going to work with. So like that data set that I showed up before that I have 3 columns, 3 headers. So let's assume that the first line still capture what? 3 of them. We have not reduced the what? The dimension. So we rule again, and it reduces what? From 3 to what? To 2. Then we rule again. The more we rule, we are not going below what? That 2. Then we work with the 2. That is the highest reduction you can get. That is the logic behind it. So it's going to be doing this on its own. It's just for us to know what is happening. That is why we are studying, we are going through this entire theory. Now, this is another line. Here is another line. And then looking at this line, you can see that what? This has captured more points and the value has also increased. So the points are even more what? Spread out now with this line. So here, the line captures the widest spread in our data. Still explaining. Then here, so remember the step, I gave us about 5 different steps, right? So step 4 here, repeat the step 3. There is a place where I say what? To repeat what? Step 3. So that's where we are now. So repeat step 3 until you have as many pieces as original what? Column. So we cannot draw another perpendicular line in a 2-dimensional space. So we are all set. This is what I will say. You can see it now. You draw all the line. You cannot draw another line. So once you get to this point where it is discovered that it can no longer have another line, then it goes with what? Whatever it must have obtained. So in practice, professional advice, in practice, these steps are completed using a linear algebra technique called what? How do we pronounce the Eugen decomposition? Eugen decomposition. So that is in practice. If you are using the algebra, that is what is going to translate into. So please, I would like us to write notes on this. Take this particular note. All right, so this is still trying to explain. Now here, step 6. To reduce the dimensions, keep a subset of principal components. For example, remove PC2 and project the point onto what? PC1, which is your new S what? Axis. So how is that achieved, or how would that look like? So you can say it now. So this is still diagram to explain what that step will be doing. So by using principal components analysis, we have reduced the number of column dimensions in the data while losing a little what? Information as possible. PC1 capture information about both X and Y, but all within one dimension instead of what? 2 dimensions. So this is what we have achieved so far. This is still explanation of it. So here, this is where we start looking at how you can implement the whole concepts we are talking about in Python. So you can use sklearn PCA. So you can see that is going to be the function that will be used to perform all the grammar we are discussing to apply the principal component analysis algorithm. So like I said, the essence of this is for you to be aware as a data scientist that you have all these libraries and you have these functions which can help you to reduce the dimension of your data. And remember, we have highlighted so many benefits and use cases of this entire concept. So we are going to start by importing sklearn. Sorry, we are going to start by importing decomposition from sklearn rather dot decomposition. We are going to import the PCA, and then we will now store the function in an object called PCA. Remember that it is case sensitive. The PCA is capital letter, but where I am storing it as an object, it can be any case. So PCA, what will be specified inside it from what I've explained so far? Who can tell us what aspect of those slides we are talking about that is represented as n underscore component equals to 2? The number of columns you want to what? Reduce the data set into. So you are the one that will specify it. So the whole of those grammar is just for you to know, okay, how it will arrive at that. But actually, you can specify it. That the whole of the data set with so number of features or columns should be reduced to 2. And that is going to be the parameter or the attribute that will do that. So there's a professional advice here. For visualization, set n underscore component to 2 or what? 3. For feature extraction, use the number of columns in your original data sets. All right, so now, once we have imported your PCA from sklearn, then remember we talk about what? Identify what? The center. From the theory, talk about what? The center before ruling what? The line. So this is where you center the data. And to center the data, you create an object and you are subtracting the mean of the data from the data itself. So you need to center each column around 0 before what? Applying a PCA model by either 1, subtracting the mean from each value, or standardizing the column. So the data here is the name of the data set we are working with. The minus here is the data then dot mean, just like what I've explained here. And then what that will do is to Remember, under standardization, what we say is standardization, the topic we have treated. Can anybody still remember? What is standardization? Is ensuring that what the entire value fall within certain range, right? Between 0 and 1. You should remember. Just like you are grouping the entire data value in a column to be between certain range, either between 0 to 1 or a hand. So that is what has happened here. So you can see that what we have here is what we have 0, we have what 1 under TV show and what video. So that is what we are doing here. Then here you are transforming, fit a PCA model on the center data. Fit a PCA model on the centered data. So here we are now using, remember the function, PCA is the object equals to the function. Then specifying the type, the number of words, the header we want to reduce to. And then after that, after saving it in PCA object, then we are now concatenating the transforming function, which is what fit to that object. And then we are supplying the data set. Data underscore center is now the what? The standardized data that you are applying into the PCA function. So professional tip here, if the columns are on very different scale, it is recommended that you scale the data as well, which is something that standardization take care of. So this brings us to the end of the theory. So what we are going to do as the practical is to give us the data set, then create a new notebook, then call the data into the notebook, like I've highlighted. Let me see if let me allow you to finish writing. And then we will now stop there. So our next class will just focus on the entire process, practical wise. I don't want to mix them together. I just want us to achieve the theory aspect. And then the next class, we just know that, okay, we now have knowledge of the concepts, then we just focus on the practical.